Assalamu alaikum and a very warm welcome to my channel. Today we are going to discuss about the sources of error, and in order to understand the sources of error, I will give you the answer of two major questions. Number one, that from where we get the errors, what are the basic sources from where we get an error while creating a mathematical model, and secondly, how to reduce these errors. So let's start with modeling errors initially. So, these errors occur when we create a mathematical models to represent real-world phenomena. Models are simplifications of reality and they often involve assumptions that may not hold true in all cases. For example, if you are modeling the motion of a pendulum, you might assume that air resistance is negligible. While this assumption simplifies the math, it can lead to errors if air resistance actually plays a significant role in your experiment. Secondly, if we look at the second example, then for the second example, we have a weather prediction. So, models used to forecast weather rely on simplification of atmospheric processes. These simplifications can lead to errors in predicting things like rainfall or temperature. So next is most important thing is that how can we minimize modeling errors? So number one, validate your models with experimental data. Number two, refine your assumptions to better reflect reality. And number three, use more complex method when necessary, but be aware of the trade-off between complexity and the computational cost. Next, we will talk about the data error, this one. So for the data error, there are errors that occur during the process of collecting data. Data error can arise from a variety of sources such as faulty instruments, environmental condition, or even the way measurements are taken. For example, imagine you are using a thermometer to measure the temperature of a liquid. If the thermometer isn't calibrated correctly, it might give you a reading that's constantly too high or too low. That is a data error. If you take another example in environmental factors, if you are measuring the length of the metal rod, changing in temperature can cause the rod to expand or contract, so leading to an inaccurate measurements. So how can we minimize the data error? So firstly, regularly calibrate your instrument. Secondly, take multiple measurements to ensure consistency. And thirdly, control environmental factors as much as possible. Okay, so next discuss about the human error. We call it blunders. So these are the mistakes made by the individuals during data collection, analysis, or interpretation. Human error can range from misreading an instrument to entering data incorrectly into the spreadsheet. For example, if you are recording the weight of an object and you accidentally write down 5.2 kg instead of 5.3 kg, that's a human error. Now, how we are going to minimize the human error? Firstly, provide proper training to those involved in data collection. Secondly, double check measurements and data entries. And thirdly, automate processes where possible to reduce the chance of the human mistakes. So all these errors combines and they call it inherent errors, and we discussed that how inherent error can be reduced. When we minimize the inherent errors, then a mathematical model is created, and after the creation of a mathematical model, we will allow to apply the numerical methods. And from the numerical methods, we got a truncation error, and on the second side, we applied the computer arithmetics, and from the computer arithmetics, we will get the round-off error, and all these errors combines to form a numerical errors. Now let's discuss in detail that what is a truncation error and how we are going to minimize it, and what is a round-off error and how we are going to minimize it. So let's talk about the truncation error. Firstly, we are going to define that what is a truncation error. So it is an error due to truncating a process involving infinite number of steps to finite number of steps. For example, consider a Maclaurin series of e raised to the power x that is equals to 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x4 by 4 factorial plus x5 by 5 factorial and up to so on. So we cannot use the infinite term. We can say use only first four terms. So for example, for the first four term, if we are going to truncate this e raised to the power x series to first four term, then it will be then it will be 1 plus x squared by 2 factorial plus x3 by 3 factorial. So that is the first four terms of e raised to the power x. So if we are going to find out the truncation error, we will find out like this, that truncation error is equals to e raised to the power x minus the truncated series, that is 1 plus x squared by 2 factorial plus x3 by 3 factorial. So from here, when we are going to subtract it, we will get x raised to the power 4 over 4 factorial plus x raised to the x raised to 5 over 5 factorial and up to so on to infinity. So that's all include in the truncation error. So that's how we get the truncation error. Next, we are going to discuss about that how we are going to minimize the truncation error with the help of a very simple example. So we are choosing an example that for the example, we are going to estimate e raised to the power 0.5 for different number of terms. And we are calculating the percentage error. And we have an exact value of e raised to the power 0.5 is given up to 5 decimal places. And that is 1.6482. Now we are going to choose the different terms and we are going to just see the variation in 5 terms, that how this truncation error will reduced by increasing the number of terms. So for the first case, we have the Maclaurin series of e raised to the power x is 1 plus x squared by 2 factorial plus x3 by 3 factorial plus x4 by 4 factorial plus x5 by 5 factorial and up to so on. So if we choose the one term, for the first case, we are choosing the one term. So for the one term, we have e raised to the power x that is equals to 1. And if we substitute 0.5, because we are going to estimate e raised to the power 0.5, so that is equals to 1. If we choose two terms, then e raised to the power x is equals to 1 plus x, and that should be equals to e raised to the power 0.5 and 1 plus 0.5, so that is equals to 1.5. That is the one term answer and that is the two term answer. Then we are considering the three terms. E raised to the power x 1 plus x squared by 2 factorial, and for e raised to the power 0.5, this is 1 plus 0.5 plus 0.5 whole 2 over 2 factorial, and the answer should be 1.625. Okay, let's choose the four terms. So 4 terms is equals to e raised to the power x 1 plus x squared by 2 factorial plus x3 by 3 factorial. So for that case, we have 1 plus 0.5 plus 0.5 whole square by 2 factorial plus 0.5 cubed by 3 factorial, and that is equals to 1.645832. Okay, let's choose the 5 terms. So we have e raised to the power x 1 plus x squared by 2 factorial plus x3 by 3 factorial and plus x4 by 4 factorial. So for that case, e raised to the power 0.5, 1 plus 0.5 plus 0.5 square over 2 factorial plus 0.5 cubed by 3 factorial plus 0.5 raised to 4 divided by 4 factorial, and when we are going to solve it, we will get 1.64843617. Next, we are going to develop a table and find out the absolute error, and then we are going to see that how the truncation error reduced. So for that, I'm going to create a table here. For the first case, I am choosing the number of terms, In the next column, we have estimate e raised to the power 0.5. And in the next column, we are going to find out absolute error because the actual value is given. Absolute value or absolute error, that is the same thing. So actual value is given, so we are going to subtract the actual value minus approximated value. So for the first term, we have the answer 1. For the two terms, we have the answer 1.5 that we calculated here. For the three terms, we have 1.625. For the four terms, we have 1.645832. In the second case, we have 5 terms, so that is 1.64843617. So when we are going to calculate the absolute values, so first absolute result is 0. Because the absolute value is given up to 5 decimal places is 1.64872. That is an actual value, and these are the approximated value. So when we are going to subtract it, we will get 0.64872. Next, we have 0.14872. In the initial case, we have subtract 1.64872 minus 1. In the second case, we have a mod here also. In the second case, we have 1.64872 minus 1.5, and we will get. And similarly, we are going to replace next values. So I'm going to write the direct result, 0.02372, 0.00289, and then we have 0.00028. Okay, if we see when we choose the one term, the error is 0.64 and up to so on. When we choose the two term, the error is 0.1. When we choose the three terms, the error is reduced to 0.02. When we choose the four terms, the error is reduced to 0.002. And when we choose the five terms, the error is reduced to 0.0002. It means that in order to reduce the truncation error, you need to choose a maximum number of terms. So if you are choosing the maximum number of terms, your truncation error will be reduced. And if you choose a minimum number of terms, your truncation error will be increased, or vice versa. Next, we are going to proceed towards the round-off error. So in order to understand the round-off error, first of all, we need to see the floating point numbers. So next, our discussion is round-off error. So in order to discuss the round-off error, we need to first understand the floating point number. Floating point number. Floating point numbers is basically used when we come up with a very small numbers or a very big number. So first of all, we see the syntax of a floating point number. So syntax of a floating point number is any sign plus or a minus. Then you have a significant. Then multiplication. Then you have a base. And then in the power, you have a plus or minus any sign. And then you have an exponent. So if we have a very small number, for example, we have a very small number, and this is 0.12345678910 zeros, and then we have a 5. So in floating point number, we wrote it 0.5 multiplied by 10 raised to the power minus 10. Similarly, if we have a very big number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we are going to write it like this, 5 multiplied by 10 raised to the power 10. Now this is a significant, this is a multiplication, this 10 is a base, and this 10 is the exponent part. So we have some rules of writing the floating point numbers. Let's discuss the rules. We call it a normalization rules for floating point numbers. So the very first rule. The first rule says that the integer part should be 0. Second rule says that after your integer part, d1, d2, d3, and up to so on to dn, this d stands for digit, into base, and you have the exponent part, then d1 must be greater than 0. Now, if we write few examples in front of you, for example, we have the first case is 0.123 into 10 raised to the power 4. Now, the integer part is 0, that is fine. And the first digit, that is D1, is greater than 0. So this is the floating point number. This floating point number basically follows the rule of normalization. If we choose the second example, we have 0.0123 into 10 raised to the power 6. So in that case, we have the integer part is 0, but the d1 is not greater than 0. So this floating point is not follows the rule of normalization. Number third, we have 1.23 into 10 raised to the power 3. So in that case, our integer part is not 0. So even this will not follow the normalization rule. So basically, the benefits of writing a floating point number is that we have few representation techniques that needs to be followed according to the IEEE floating point standards, that is Institute of Electrical and Electronics Engineering. We have IEEE, that is basically the Institute of Electrical and Electronic Engineering. That have floating point standards. And according to these standards, we have two types of systems. Number one is the single precision. And in single precision, we have a 32-bit PCs. And in 32-bit PC, we have a 1-bit allow for sign. If it is negative, it uses a 1-bit, and if it is positive, it will not be using any bit. Next, we have the exponent part, and the exponent part should be uses 8-bit. Maximum allowed is 8 bits. Next, we have the fractional part, and the bits allowed to fraction is 23 bit. If the number is greater than 23 bits, then definitely it will automatically round it off. Secondly, we have a double precision. And the double precision, we are allowed 64 bits as a whole. So for the sign, they use 1-bit in case of a negative, and it will not use any bit in case of a positive. Next, we have the exponent part, that is allowed 11 bits. And if your exponent part is more than 11 bits, then definitely it will be rounded off. And for the fraction part, it will allow 52-bit. And for the 52-bit, if your number is fractional part is greater than 52 bits, then definitely it will be rounded off. So that's why we will go for the floating point number. If we have a very small number, or if we have a larger numbers, then definitely we will convert it into a floating point number instead of ignoring this round of errors, right? Next, we are going to discuss about the last concept, that is chopping versus rounding, and which one is most better when you are going for by hand calculations. So chopping versus rounding. In order to understand this concept, I'm using an example of E. That's value is 2.7182845, and similarly for the rounding we are using the same example, 828182845, and up to so on, right? Now, in order to understand the concept between these two, we need to chop the number to 7 significant digits. So for chopping, we avoid the rounding. We directly chop the number like we have a 7 digits. So that should be 1, 2, 3, 4, 5, 6, 7. So we just chop and write it 2.718281. For the rounding case, to 7 digit, we write it to 7 rounding. So we need to write 1, 2, 3, 4, 5, 6, 7. So as the eighth number is greater than 5, so that should be increased to 2.718282. So when we are going to find out the error, this is the actual value and this is the approximated value. So in that case, the error will be equals to 8.2844999 into 10 raised to the power 7, -7. That is an error for the chopping if we chop the numbers. So in case of a rounding, the error should be equals to -1.715499 into 10 raised to the power -7. So if you look at the difference between the chopping and the rounding error will be lesser than the chopping error. So whenever you are doing by hand calculation, so most preferable is to go for rounding instead of chopping. So that's all for today. Thank you so much for watching. Don't forget to subscribe my channel. Take care of yourselves and Allah Hafiz.